Okay, so hello everyone. Let's begin today's lecture. So we'll continue with the counting module. So today what we will do is we will look at this principle of inclusion-exclusion. We will see what that means and some applications of this principle in counting the number of onto functions between two sets. And we will see what is called a derangement. Okay, so we will see that. So let's first start with what is this principle of inclusion exclusion. So let's start with a small example, or rather a smaller version of this. So this we know, like, so I'm given two sets, A1 and A2. I want to find the number of elements in A1 union A2. Okay, so we have seen this as the subtraction rule. So how can we do this? So first, if I count mod A1, this will give me all of these elements. Okay, then if I add mod A2, I will get all these elements. But there are some elements which are being double counted. What are they? They are these elements. An element which is there in A1 intersection A2 will be counted here as well as here. So in order to get the real count, what we should do is we should subtract mod of A1 intersection A2. So this will give me the exact number of elements in A1 union A2. So this we have seen earlier as the subtraction rule. So what we are going to do now is to generalize this to larger sets. Okay. So let's start with size 3. Okay. I'm given 3 sets, A1, A2, and A3. Okay. So now what do we do? Maybe I'll draw it a bit better. Okay. Not much. So now I want to count the number of elements in A1 union A2 and union A3. And I don't want to double count anything. Okay. So first, the strategy will again be, let me just add the set of all. If I do this, okay, look at an element here in green. It will be counted only in A1. So it will be counted only once. Similarly, an element 8 in this part will be counted only once, and an element here will be counted only once, because this will be there only in A3. Now, suppose I look at an element here. Okay, so this is in A1 intersection A2. So that will be counted once here and once here. Okay, so this element will be counted twice. Similarly, an element here will be counted twice, an element here will be counted twice. And finally, If I look at an element here, it's present in A1, A2 and A3. So it will be counted 3 times. Okay. So what is happening is if I just do A1 plus A2 plus A3, these elements are counted twice and these elements are counted thrice. So we need to discount for this. Okay. What do we do? So let me first subtract A1 intersection A2. Now what does this do? This will make sure that these elements which were counted twice will now get counted only once. Okay. I'll do the same for A2 intersection A3 and A3 intersection A1. If I do that, we will get this, oh, sorry. This will get counted only once because an element here will get counted once in A1, once in A2, and then it will get subtracted once by A1 intersection A2. Okay. An element here will again get counted once, an element here will again get counted once. But what about this part? Okay. See, an element here is present in A1 intersection A2 and in A2 intersection A3 and in A3 intersection A1. So what will happen if you do the subtraction? The elements in this part will not get counted at all. I mean, they will just get subtracted multiple times, and then you will have it won't be counted anywhere. So you have to add them back, and that is where you do plus mod of A1 intersection A2 intersection A3. Okay. Is this part clear? Can you say yes if you have understood this?
Yes.
Okay, so I can type in the chat. Okay. Okay, good. Okay, so there is some. I'll repeat the last part. Okay. See what yeah. So some of you want me to repeat the last part. Okay, wait. I'll do that. See, up to this was the first. No, I mean, if I do up to this. Okay, let me know. No, if I just do this, A1 plus A2 plus A3, the elements here will be counted here as well as here. So that is 2. Similarly, 2 here, 2 here. And the elements here will get counted here, here, and here. Okay, that was the point. Now you have to subtract these extra counts. So that's why I subtracted A1 intersection A2. So an element in A1 intersection A2. See, how many elements are getting counted twice I mean, how many elements of this kind are getting counted twice here? The ones in A1 intersection A2. Okay. So I subtract mod of A1 intersection A2 so that, okay, I'll do it in steps. Here this 2 becomes 1 when I subtract A1 intersection A2, and this 3 becomes 2 because these are also there in A1 intersection A2. Then when I subtract A2 intersection A3, this 2 becomes 1, and this existing 2, I mean the 3 which became 2 will now become 1. And when I do this 2 becomes 1 and this 1 becomes 0. So in some sense, we are now undercounting. We are not counting these elements at all. So you just add them back. Okay. So I think if you have trouble understanding this, you should just take 3 sets, okay, with intersections, and then see what happens when you do step by step what happens. Like if you do this, what are the things you're counting? If you do subtract this, what are the things you're counting, and so on. Okay, good, fine. So now that, can you try to find the expression for this 4, A1 union A2 union A3 union A4. So I'll give you a couple of minutes. Okay, so some of you have given answers. So one thing, it will be difficult to draw a Venn style diagram for this. Instead, we need to kind of generalize the expression that we have before. Let me write down the expression and then we will see why it is correct. Okay. So as usual, you start with A1 plus A2 plus A3 plus A4. Okay. You do this. Then you look at all intersections pairwise and you subtract them. Okay. Because they have been counted twice. Okay. The intersections A1 intersection A2 has been counted both in A1 as well as in A2. So I'm subtracting. And I'll do A1 intersection A3, A1 intersection A4. Similarly, all the two intersections, A3 intersection A4. Okay. But I'm not done yet, because what will happen is, if I look at elements which are there in three of them, say for example, they are there in A1, A2 and A3. Like in the previous case, they would have been, so consider an element in A1 intersection A2 intersection A3. It's counted 1, 2, 3 times. Okay. And then what happens? I mean, how many times is it getting subtracted? It gets subtracted once in A1 intersection A2, A1 intersection A3, and then in A2 intersection A3. I have not written that. So it gets subtracted completely. So you need to add it back. So then I'll add all the combinations of three sets. A4 plus A2 intersection A3 intersection A4. So I added back. But now if I look at an element which is there in all the four sets, okay, what happens? So let's see. So I'll write it here. So let's take an element A, which is there in A1 intersection A2 intersection A3 intersection A4. It gets counted once here, once here, once here, once here. Okay. And then, so how many times does it get subtracted? There are 4 choose 2, which is 6 times it gets subtracted. So there'll be a minus 6. And then how many times does it get added back again? There are 4 choose 3, there is 4 times. So it gets added back 4 times. So what happens here? This is 4 plus 4. 8 minus 6, 2. So it's getting counted twice. So you need to subtract once. And so you will get a final minus A1 intersection A2 intersection A3 intersection A4. Okay. So this is the expression for 4 sets. So let me give you an idea of what is happening. Like in general, we are interested in looking at an expression for A1 union A2 union n sets. Okay. Now, oh wait, is there some? So I did not write some of them. 4 choose, wait, did I write 4 choose 3 should be, yeah, I missed one thing. Sorry. Which one? Which one did I miss? A1, A2, A4. Okay. So in general, okay, now if I want to do this, let us look at how the pattern looks like. I mean, you first add all the one element, I mean, all the sets, then you subtract all the intersections of 2, then you add all the intersections of 3, then you subtract all 4 intersections and so on. So suppose we just generalize this, what expression we will get? This will be sigma mod AI, okay, minus sigma all pairs plus sigma, if I take I, j, k, all triples, and so on. And at the nth thing, what should I have? So at 2, I have a minus. At 3, I have a plus. Okay, so if n is odd, I have a plus, and if n is even, I have a minus, the sign. So I should have plus minus 1 power n plus 1. Okay, if n is even, I want a negative sign, and if n is odd, I mean, it's not n, I mean, yeah, correct. So if n is odd, then I need it to be plus. So that's why I do minus 1 power n plus 1 mod of a1 intersection a2 intersection all of them. Okay, so substituting n equal to 4 gave the previous expression, substituting n equal to 3 gave the one for 3, and so on. Now, why is this correct? Okay, so
Anu sir,
yes,
shouldn't we add one condition like I not equals to j and I not equals to j
yeah,
equals
yeah,
to?
yeah, I kind of assumed that. So you're right, you're right. Yeah, so this is all intersections of 2. Yeah, so this is I not equal to j, because then we are again looking at ai here, which is not correct. So they are here again, I not equal to j not equal to k, and so on.
You can more simply write 1 less than equals I less than j less than equals n.
Yeah, agree,
And in
totally
the
agree.
next one,
Yeah,
1 less than I less than j less than k less than equals, so on.
absolutely, yes, yes, I agree with you. So you can also do this. So 1 less than or equal to I less than j less than or equal to n. 1 less than or equal to I less than j less than k less than or equal to n. Yes, I agree with you. Okay. So yeah, now the question is, why is this correct? Okay. One second. Okay. So we want to say that every element, why is this correct? So we need to show that every element A in A1 union A2 union AN is counted exactly once. If we do that, then this expression is giving us the actual value of A1 union A2 union AN. Okay. Now let me pick an element A. So this A will be in some sets and it will not be in some sets. So suppose A is in A1 intersection A2 intersection AJ, and A is not in the other sets. Okay, A is not present in other AKs. Okay, now we will say that this A is counted exactly once. Okay, so why so? Now see, if I look at this part, okay, A will be counted j times. Okay, if I look at in mod AI, A is counted j times. Okay, if I look at AI intersection AJ in this pairwise things, how many times is A subtracted? So, and it is subtracted in how many pairs are there? J choose 2. Okay, in so many intersections, you will see that A will be present and it is subtracted. Now, what about if I look at AI intersection AJ intersection AK? It is now added J choose 3 times and so on till it goes up to J minus 1 power J plus 1, where you will hit A1 intersection A2 intersection till AJ up to that. Beyond that, it will not be present in any intersection because A is not present in any other sets. So all intersections which have more than J elements, A will be absent. Let me write it here. Continued. So in all intersections of more than J plus 1 sets, A is not counted. Okay. So the expression giving the count of A is this thing. It is J choose 1 minus J choose 2 plus J choose 3. So it is J choose 1 minus J choose 2 plus J choose 3, so on, plus minus 1 power J plus 1, J choose J, okay, which is just 1. Now, what is the value of this expression?
0.
Which means A is not counted at all. We need it to be 1. Okay, because
it is 1 only because we are not counting JC0 here. Had it been
exactly.
JC0, then it would have been 1.
Yeah. So the value of this expression is 1, but can you all think about this? Why is it 1?
It's a binomial expansion of 1 minus 1 to the power.
Exactly. So if I look at the binomial expansion of, say, so first let me recall the binomial expansion of x plus y power n was what? Sigma n choose j, x power n minus j, y power j, where j, okay, I should not be using j again. Just to, minus I y power I, where I goes from 0 to n. Okay. Now, if I put x equal to 1 and y equal to minus 1, I will get 0 equals sigma I equal to 0 to n, n choose I, this 1 power n minus I will just be 1 times minus 1 power I. So what is this? This is, if I just expand it, if I look at n 0, minus 1 per 0 is just 1, minus n1 plus n2 and so on till minus n3 till minus 1 power n nn. Okay. Now, if I bring this part to the left hand side, I will get, this will imply n1 minus n2 plus n3, so on. Since the minus comes to this side, it will become minus 1 power n plus 1 nn equals n0, which is just 1. Okay, so The point is, if I take some element A in this union, it will be part of some J sets. Okay. And if I look at the expression and then I see how many times it gets counted, I get this expression, which turns out to be 1. Okay. So every element is counted exactly once in this expression. So this gives us this expression for mod of A1 union A2 union AN, which is called the principle of inclusion exclusion, this expression. Okay. It's just a matter of you include, exclude, include, exclude in the right way possible so that the final count is what you want. Okay. So is this expression clear, how we derived it and why it is correct? Please type yes if you have followed it. Okay. Okay, good. So several of you have understood. Okay, good. So let me continue. So if we have not understood it yet, please go through the text and then you let me know if there is any trouble. Okay, so was there a question? No. Okay. Good. So now I will pause for a question. Okay, please try out this problem.
Okay, cool.
Sorry, is there a question? Okay, yeah, I've got several different answers. So let's try it out. Okay, sorry. So I want to count the number of bit strings of length 8 with at least with 6 consecutive zeros. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 positions. Now the 6 consecutive zeros can either start from here or start from here or start from here. So I will, okay. So let me just say A1 to be the strings of length 8 such that, okay, that start with 6 consecutive zeros. Okay. Now what is A2? Strings again of length 8 that start with 1. No, sorry. That have 6 consecutive zeros starting from position 2. Okay, and finally A3 is a set of strings that have 6 consecutive zeros starting from position 3. Okay, now if I have 6 consecutive zeros, it should either start from position 1 or 2 or 3. Okay, there can be more zeros, that's fine, but these are the only 3 starting possibilities. I mean, you cannot have 1 followed by 0, 0, 0. That doesn't have okay. So now the required answer is mod of A1 union A2 union A3. Okay, so now once again let's use the principle of inclusion exclusion. So what is mod A1? So the set of strings that start with 6 consecutive zeros here, which means the position 7 and 8 can either be 0 or 1. Okay, so there are 4 options. What about mod A2? It says that here they should contain, this should have zeros, which means 1 and 8 are free. So once again there is 4, and then mod A3 is once again 4, but there is a lot of double count. Essentially what we have to do is, now we have to find what is A1 intersection A2. Okay, see what is A1 intersection A2? It should have a 0 here as well as a 0 here. Okay, which means at this position it is free. So there are 2 choices. Is 2. What is A1 intersection A3? It has to start with, I mean, so this one has, sorry, this part has to be 0 and this part also has to be 0, which means there's only one option. This is 1. And what about A2 intersection A3? Okay. Now what is A2 intersection A3? It is 0 here as well as 0 here, which means here it is free. So there are 2 options. Now what about A1 intersection A2 intersection A3? Everything should be 0 and there is only one option. So now if I do the expression, it will be 4 plus 4 plus 4. I'll write it down. So required thing will be 4 plus 4 plus 4 minus 2 minus 1 minus 2 plus 1. So what do I get? So this is 12, 10, 9, 7, 8. Okay, so the final answer is 8. Is this
Excuse me, sir.
yes?
Sir, here why are you including zeros also? Like that would be 7 consecutive zeros, na? But we want only 6.
No, no, with at least 6 consecutive zeros. I mean, if I have 0, 0, 0, 0, 7 zeros, doesn't it have 6 consecutive zeros?
But the question says 6 consecutive, not at least 6.
No, no, no. Okay, wait, wait. So does the string have 6 consecutive zeros?
But we want only 6 or at least 6.
No, no, no.
Like,
Does this string have 6 consecutive zeros?
yes, it does.
Yes. So that is the point. So even if the question, I mean, there is an at least which is hidden in this question, but I don't think it is necessary for this question. So how many bit strings of length 8 contain 6 consecutive zeros? There's a contain. So, and does this string contain 6 consecutive zeros? Yes. A string with 7 zeros contains 6 consecutive zeros. Okay. So, you understand? This at
Yes,
least
sir. Yes.
is understood, and I don't think it is needed. Okay.
Okay.
Yeah. Okay. Yes, yes. So is this part clear? Like this is an application of the principle of inclusion exclusion. Okay. So let me continue. So now we are going to look at another application of principle of inclusion exclusion. We want to look at the number of onto functions from a set with m elements, say 1, 2 till m, to a set with n elements. Oh, I don't remember. Okay, fine. Okay. Now, how many? So we have seen what is the total number of functions that will be. See, this thing can be mapped to any of the n elements. There is n into n into n into so on n m times. So this will be n power m. That is the total number of functions. We have also seen what is the total number of onto function, one functions. So if I get this is okay. If I have n, then for the second thing, I will have n minus 1. For the third thing, I'll have n minus 2 and so on. But now we are interested in onto functions. What is an onto function? Every element here should be mapped. Okay. So there should be a, what is this? An element in the codomain which maps to this. Okay. So you know what is an onto function. So can you think about how principle of inclusion exclusion can be used to count the number of onto functions? So take, I'll give some time, like 3-4 minutes. Just think about it, and then I will give you a solution. Okay. Okay, so let me try to explain. So how do we go about this problem? See, first, suppose we have the set of all functions. Now, what are onto functions? Every element here should have a pre-image. Now, suppose I look at the set of functions where at least one element, so I'll call this set A and call this set B, of B has no pre-image. Okay, what we need is this part. These will be the onto functions. So now I know a value for set of all functions. Now if I can get a count for the set of functions where at least one element has no pre-image, then I can take this and subtract this from it. This will give me a count of the number of onto functions. So this is what we are going to do. And here is where we will use this principle. Okay. So let us define, say I have used A here. I'll call Ci to be the set of all functions where element I has no pre-image. Okay. Now what we need is the count of C1 union C2 union Cn. Clearly there will be functions which are present in both Ci and Cj, Ci and Cj and Ck and so on. And here is where we will use our inclusion exclusion. What is this? This will be sigma mod Ci minus sigma mod Ci intersection Cj plus sigma mod Ci intersection Cj intersection Ck and so on, plus minus 1 power n plus 1 C1 intersection C2 intersection Cn. Okay. Now what is mod Ci? These are the set of all functions where I has no pre-image. So I will have to leave out I. This is I. I'm assuming that I is not there. And then I can map any element here to rest of the elements. Okay. So that will be what I have. So 1, 2, 3 till m. For each of them, I have n minus 1 choices. So n minus 1 into n minus 1 into n minus 1. So this will be n minus 1 power m. Now, what is mod of Ci intersection Cj? Here, I and j have no pre-images. So it's like eliminating I and j from the picture. So this will be n minus 2 power m. Okay. And similarly, Ci intersection Cj intersection Ck will be n minus 3 power m. Okay. So what will the final answer be? So this one will be n choose 1 times n minus 1 power m. This one will be n choose 2 times n minus 2 power m. This is n choose 3 times n minus 3 power m, so on. Now, the final thing is 0 because we cannot have a function without a pre-image. We cannot have a function where every element has no pre-image. Okay, so this part will be 0. The n minus 1th thing will be what? That will be n choose n minus 1 n minus n minus 1 power n. Okay, so this gives us the required expression. As I said before, you take the set of all functions, which is n power m, and subtract this expression from there. So you will get n power m minus whatever expression we have. Okay. So that's all. This gives us the set of the number of onto functions from one set to another. Okay, and we have just used principle of inclusion and exclusion. Okay, so can you say yes if you have understood this, please? Okay, so is there any question here? Okay, so then I'm continuing. Okay, so just this is just more or less vanilla usage of principle of inclusion exclusion. Okay, right. So let's go to the next application of principle of inclusion exclusion, which is derangements. So what is a derangement? So we have seen arrangements. What is this? What is a derangement? It's a permutation of objects such that no object is in its original position. So I'll give you an example. So if I look at 1, 2, 3, what are its permutations? Its permutations are 1, 3, 2. Okay. So then I have 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So I have how many? 1, 2, 6 of them. But now, so this was my starting point. Now look at this thing. So 1 is in its original position. This is the original position. In this thing, 3 is in its original position. Okay. Whereas in this thing, 2 is in its original position. Okay. Whereas if I look at this thing, none of them is in its original position. All of them have been swapped. Okay. Similarly, here also, all of them have been swapped. So these two are derangements. Okay. Now, once again, now the question, so this is for 1, 2, 3. Similarly, you can look at 1, 2, 3, 4, and so on. Now it's interesting to get an expression for the number of derangements of n objects. Okay. Once again, we can try to use principle of inclusion exclusion. Can you think about this? I'll give some time. So look at this question. If you have not understood what a derangement is, please let me know. Yeah, so let me give you the answer. So what do we want? So first of all, we know the number of total. So if I'm okay, what is this? So if I start with let me- number of derangements. See, I'm starting with 1, 2, 3 till n, right? I have total number of permutations is n factorial. Okay, and out of that, some of them are these derangements. So what is special about these places? At least one element is in its original position. Okay, so and then this is where we use inclusion exclusion. We define AI to be the set of permutations where I is in original position, that is the ith position. Okay, which is ith position. And then what we need is mod of A1 union A2 union AI will give us the green part. So all we need to do is do n factorial minus this green part. Okay, so how does it go? So what will mod AI be? So you are fixing I, and the rest of them can be permuted in any number of ways. That will be n minus 1 factorial. What is mod of AI intersection AJ? You are fixing I and J. The rest of them can be done in n minus 2 factorial and so on. Finally, if you fix AI okay. Now, if I look at this thing, what will that be using inclusion exclusion? So mod of A1 union A2 union AN will be sigma AI, which will be n1 n minus 1 factorial minus n choose 2 n minus 2 factorial plus n choose 3 n minus 3 factorial and so on, plus minus 1 power n plus 1, where all of them are in one position. That will be 1 factor. Okay, and the final answer, total number of derangements, will be n factorial minus this. Okay, so that gives us this thing, n factorial minus n choose 1 into n minus 1 plus n choose 2 into n minus 2 and so on. Okay, that is all. So you can simplify it further. Okay, and you get a nice looking term. Okay, fine. So that's all. This is an interesting use of inclusion exclusion. So let's kind of, this is the last part of the lecture. So here is a problem. Just think about it for like some 5 minutes and then I will give you the solution. Yes, non-negative integral solutions. Yeah, so how do you go about this? So I just do this again. So first of all, if I look at the total number of solutions, just solutions to x1 plus x2 plus x3 equal to 15. These will be triples, right? Something like say 1, 1, 13, and so on. Things like this. Now, sum of them is the required thing. And what is that? My x1 should be less than or equal to 4, x2 should be less than or equal to 8, and x3 should be less than or equal to 7. Now, what about the other part? In this part, either x1 is bigger than 4, or x2 is bigger than 8, or x3 is bigger than 7. Right? So this gives us an idea to use inclusion exclusion. So let's define A1 to be the set of solutions with x1 bigger than 4. Okay. A2 to be the set of solutions with x2 bigger than 8. A3 is the set of solutions with x3 bigger than 7. The required answer is total number of solutions minus mod of A1 union A2 union A3. Now, total number of solutions, we have seen how to do this in the previous class. Okay. Now, if I want to find the set of solutions with x1 bigger than 4, what should I do? Okay, let's first look at the total number of solutions. Sorry. This is what x1 plus x2 plus x3 equals 15. So total number of solutions. So what do? We have 15 stars and 2 bars, right? Sorry, 2 bars and 15 stars. And then we have to count the number of, this will be number of, so this will be 17 choose 2. Okay, good. Now, number of solutions with x1 bigger than 4, which means somehow my x1 is of the form 4 plus x1 prime. Okay. So I want to find the number of solutions to 4 plus x1 prime plus x2 plus x3 equals 15. That is, I want to find the number of solutions to, and this will be what?
It should be 5 plus x prime, x1 prime.
Sorry, you are right. Thank you. So this is 5 plus x1 prime. This is also 5. And so this will be 10. And so this will be like 2 bars and 10 stars. This will be 12, choose 2. Okay. Then what is number of solutions with x2 bigger than 8? If you do a similar reasoning, what will you get? So you want to find x1 plus x2 prime plus x3 equals 15 minus 9, that is 6. So this will be 8, choose 2. And finally, number of solutions with x3 bigger than 7. X1 plus x2 plus x3 prime equals 15 minus 8, which will be 7. This will be 9, choose 2. Okay, good. So the total thing is 17 choose 2 minus 12 choose 2 minus 8 choose 2 minus 9 choose 2. Wait, no, absolutely not. No, no, it's not over yet. This is, so this is just mod A1, this is mod A2, this is mod A3. Okay, so now you have to find mod A1 intersection A2 and so on. Excuse me. So it requires some more calculation. I'll let you do it. So mod of A1 intersection A2 should be like you have 5 plus x1 prime and 9 plus x2 prime. And then you will get some number. Okay, so continue the calculation. Okay, I'm not giving the final answer, but you get the way to do it. Okay, so that is all. Now let me summarize what we did. So this is also the last class for the counting module. So today we have seen the principle of inclusion exclusion. We have seen the expression for it and how we derive it, and then we have seen its use in finding number of onto functions and number of derangements. Okay, so this brings an end to the counting module. The next thing will be logic. We will see. So tomorrow there is a tutorial, right? And then either Thursday's class will be one problem session, or I will start with logic. Okay, so there will be something on Thursday, so I will confirm. Please do attend tomorrow's tutorial session if you have any questions. Okay, I am done. You can, the class is over. You can feel free to leave. If anyone has any questions, I'll stay back. But otherwise, the class is over.
Excuse me, sir.
Yes.
So for the derangement question, where we figured out the number of derangements, I was approaching the question in a different manner. Can you just, help me in the approach?
Okay, I'll try. Yeah.
If we consider in the similar fashion that you had, total number of ways equal to n factorial, and then we subtract, we take first condition where two of them change and the rest remain same.
How would you get this?
NC two ways, because we are choosing 2 out of n and it will be multiplied by 1 because there will be just one way. If there are m objects and m minus 2 are at same places and we just need to shift the 2, so we kind of, so that is MC two ways. Then
so these are not in, okay, so you are counting the things which are not derangements.
Yeah, just the opposite, I guess, to the to your approach. So the second subtraction would be where 3 change and rest remain the same. So this will be NC3 multiplied by 2.
Okay.
NC3 because we are choosing 3 out of n. That is the number of times we need to subtract basically because of n objects. And
okay, wait. So let me just write down what you are trying to say. So you are defining what? But wait. So you're counting the number of arrangements where 2 of them are out of place.
Yeah, 2 of them are out of place, rests remain same.
This is, so you choose which 2 and then the rest are taking their positions. Then 3 of them out of place. See, this one, three of them out of place and 2 of them out of place are disjoint.
Yeah.
So, and you're getting n choose 3 here.
Multiplied by 2. Multiplied by 2 because, so for example, if there were 6 objects, I mean 1, 2, 3, 3 objects, there will be 6 ways out of which 2 will have derangement. So multiplied by 2 here in the 3 of them
so
out
you are
of 2.
choosing I, J, K, and the number of ways in which they can be out of place.
Yeah.
Which is 2 for you here. How did you, okay, so how do you generalize this? If I have 4, so you will choose 4 of them, and then you have to put 4 of them out of place, which means you will be counting the.
I actually don't know how to generalize. That is where I
No,
needed
no.
your help. But
Yeah, because you're actually counting, what are you counting? The 4 of them out of place is what? The number of derangements of 4.
yeah. Number of derangements of 4.
But this is exactly what we want in the end. Like, you see, we want the number of derangements of n elements.
Yeah.
Okay. Yeah. So essentially, if I give dn, the number of derangements of n elements, you are kind of saying dn is n choose 2 d2 plus n choose 3 d3. Is this what your d4 n choose n minus 1 dn? Is this correct? dn minus 1?
Yeah, probably. It's kind of giving a recursive relation, I think.
So what were you saying? dn is n choose 2 d2. Can you check this out? I mean, if it turns out to be correct, then it's fine. Yeah,
I was
otherwise, yeah.
dn is equal to n factorial minus nc2 d2 minus nc3 d3.
Okay. No. So this is dn, right?
Yeah.
And then the other thing that you get is
n factorial minus nc2.
why n factorial minus? Because
These were the total.
no, these are the things. I see. Okay, right. Okay, so d2 will be. Okay. Now you need to figure out if probably both of them are the same, but just check this out. Okay, so d2 will be 2 factorial minus whatever. d3 will be. Okay.
Yeah.
Okay. So you will actually. Yeah. Can you just check it and let me know if.
Yeah. I'll check it again.
Sorry?
I doubt that is correct though.
Okay.
Because the final part of the summation shuffles around n minus 1 elements, leaving the nth element fixed, right?
Yeah.
That is true.
So
So what is going wrong here?
So
you're
this is
saying that-
basically 2 are dearranged, 3 are dearranged, up to n minus 1 are dearranged. It might be right, but something seems off.
Yeah, I'll check it again if I'll have an issue with it, I'll probably let you know.
So wait, so what is there a flaw somewhere? Where is the flaw?
Yeah, there is a flaw, right? 2 of them are out of place automatically implies that the remaining are in place, right? For these to be disjoint. But if they are in place, then they can't be a dearrangement.
Yeah,
You got
that
my
is
point?
why.
So that's what
Yeah,
she's.
that is why we were subtracting it from n factorial to find the dearrangements.
So wait.
there's
Let's try to do it again. So n factorial, she's trying to find this part.
Yeah.
So what is this part it is not a derangement, which means at least one of them is in place,
Mm-hmm.
which means at most n of n minus 1 of them are deranged. Okay.
Yeah, then this makes sense. Yeah, it might be
Okay.
right. It might be right then.
Yeah. So then this
Yeah.
is homework for you. Okay. Please check.
Yeah.
Okay.
Yeah.
And if not, find the flaw. So, okay.
Yeah,
Hello,
sure.
sir.
Yes. Yes.
I said in the last question,
Which is
like,
this thing.
yeah, x is less than 4, less than 8, and less than 7.
Mm-hmm.
Said here, if we do like x1 is less than equals to 4, that means x minus 4 is less than equals to 0.
Okay.
And if we take minus x1 plus x4 equals to capital X1, which is greater than 0.
Okay.
And summing all this will boil down to one equation like capital X1 plus capital X2 plus capital X3 equals to 4. So solving this, I think, much more easier to calculate. It is 10 and I have just calculated it accordingly, and that inclusion
Okay.
exclusion principle is also.
So, sorry, can you repeat? So you're saying that x1 minus 4 is less than or equal to 0. Now what are you doing? You're taking capital X1 to be?
Capital X1 to be minus x1 plus x4. 4 minus x1. And capital X2 to be 8 minus x2, and capital X3 to be x3 7 minus x3. Yeah.
And then we know that x1 is
I am just putting all them in 50.
no, but isn't there a, okay, wait. So x1 has a bound, no, has an upper bound.
Yeah, that is, sir, capital X1 is greater than equals to 0. Now,
Hmm. Wait. Not complete.
lower bound is there, not upper bound.
So if I look at x1 plus x2 plus x3 equal to what? I get, I mean, essentially you want, okay, you essentially want the number of solutions for 4 minus x1
Hmm.
equal to what?
Equals to 15.
Equals to 4.
Okay. So
This
because
is 4.
x1 is something before between 0 to 4,
Yeah.
so capital X1, that's what your capital X1 is. So it's something
Yes.
between 0 to
0 to the limit means the part where the right side of the equation.
yeah. Okay, I see. This is 15, and then what you get?
No, this is not 15. This is 4 because we already distributed 15 among these.
True. Yes. Wait. I need some time. So Shuli, can you? What is your? See, okay, wait. I want my x1 to be anything between 0 to 4, and x2 to be anything between 0 to 8, and x3 to be anything between 0 to 7. Okay,
Yes.
and then sum of such values should give me 15.
Yes.
So how are you getting
Yes.
it? Sorry, can you repeat?
Sir, I am just putting like x1 minus 4, that what you have written there. X1 minus 4 less than 0. So if we just invert this inequality, so minus x1 plus 4 will be greater than 0.
Okay.
So we are calling that quantity as a capital X1.
Okay. Yeah. Okay. And then I see. And this has to be here. What? So okay. Wait a minute. So now I'm confused. Wait. So then what will come on the right hand side? So because
You can directly sum this, means 8 plus 7 plus 4 is 19 minus
okay.
x1, x2, x3, that is 15. 19 minus 15, that is 4.
Okay, 19 minus x1 plus, I see.
Yeah.
Okay, I see what you mean. Okay, okay.
And these are x1, x2, x3.
Okay, okay. So you get 4 here. I see, I see. So you get.
Yeah, capital X1 plus X2. Yeah, yes, sir.
Oh, yeah, yeah. Fine, fine. Sure, sure, sure. Okay, fine. So are you getting the same answer?
Yes, sir. 62.
Huh.
62, that is coming 10.
Oh, okay. Yeah, nice, nice. Definitely. So this was given to apply principle of inclusion exclusion, but I agree that this is also a good solution. I mean, it's even easier, definitely. Okay, I agree. So unfortunately, both of them give the same answer.
Yes, yes.
Okay, good. Anything else?
Sir, in the problem of one-to function,
Okay.
um, there if I think from m element I choose n element such that first element in permutation mpn, where first element goes to 1, second to 2, and n to n, and last n element goes to n, and then rest of the m minus n element goes anywhere in this 1 from n, then that will come mpn and into n to the power m minus n. Is that will be answer?
Wait, wait, wait. So how? Okay, wait. So how are you getting the onto thing? So you want to? I mean,
I want to choose n element from those m element
okay, okay.
in permutation
Sure. Okay. So you
and
choose
then
M,
assign
choose N.
mpn
No, no, you're choosing N elements from M
permutation. I mean first element of that choose
into N factorial.
that choosing element goes to 1 in the range in the image set.
No, no, sorry, sorry. Can you repeat once again? So you have M elements
From
here. You
those
have
m
N
element,
elements.
I choose n element in order,
This
and
is M
that
choose N in M choose N ways. Huh.
in order mpn.
No, no, no. You have to choose N elements from M elements, and then you are ordering them. No,
Hmm.
correct?
Hmm.
Huh. Now, so your strategy is I will first. So an onto function. How does it look like? Each of them. No, no. But wait, wait, wait. See, an onto function means that each element here should have a pre-image, right? But maybe, yeah, of course. So there should be at least n elements here which are pre-images. This how you're doing it. So you will first choose these n elements, but there will be several counting. Wait, wait. You are choosing these n elements. Then you're doing it in different ways, and then the rest of them you're assigning arbitrarily. Is it? Who had the question? Sorry. Are you here? Hello?
Yes, sir. Sir, actually, what I'm saying that
Okay.
from element, I choose those n element in ordered manner, such that the first element of that that row will,
Actually, I don't. Sorry, I don't hear you carefully. There's some connectivity issue.
hello, sir. Hello, sir.
Yeah, yeah. Tell me.
Actually, I want to choose n element in ordered manner, and
Okay.
actually, I want to assign
Hmm.
one of the range image set. The one will come the mpn, the first element of the mpn will go to 1, and second element of the MPN will go to 2, and in this way. So and the rest of the m minus n element will go anywhere of this image.
Okay, so what is your final answer? Sorry. What is your final answer?
Dot m minus n, sorry, dot n to the power m.
Sorry, NPN dot.
Sorry, m. Sorry, not NPN, MPN.
Fine. Okay.
Dot m minus, sorry, n to the power m minus n.
I understand what you are trying to do. Okay, wait. So let's see. If I do 1, 2, okay, let 1, 2, 3, and here suppose I have 1, 2. Okay.
For on to n, m must be greater than n1.
Yeah. M must be greater than n. Yeah, for on to.
Yes, very good.
That is assumed.
Okay.
Okay. So see, so Animesh, so you will consider one. So in your MPN, you will consider 1, 2 going to this, and then in this n3 going to 1, you may consider. You will count it once. Now,
it's a one choice.
You will also do.
I also can.
One second. So
1, 3. I can first do 1, 3.
Sorry, 1 second. If I look at this, 1, 2, 3 goes to say 2. Okay. 1 goes to 1, 2 goes to 2, 3 goes to 3. See, this thing you will count. See, in this MPN, okay, 1, 1, 2, 2, 1, 1, 3, 3 will be counted twice. Because 3p2, you are choosing 2 elements out of 3 and then you are ordering them. Sorry, 3 goes to 2. 3 goes to 2. Right? You will be counting them twice.
I don't know.
And so, and the third thing, so 3 going to 2 will come here, and here again 2 going to 2 will come here. So there will be, I mean, this function will be counted at least twice. So try to do this, I think so. So you will do 3p2 times what? 2 power 1, no?
Yeah.
So what does it, what
sorry,
does it?
2 power 2. Sorry, 2 power 1. Sorry.
So what is this 3p2 is what? 6, no?
Yes.
So how many onto functions are there? So let's say 1 goes to 1, 2 goes to 2, 3 goes to 3, and 3 goes to 1. There are 2 of them. Then 1 goes to 1.
3 goes to 3.
3, that's all. Wait. So if I count the number of onto functions here, do I get 6?
1 goes to 1.
If I apply this formula, what do I get? So this will be what? N is 2 raised to 3 minus, maybe it's easier to just count the number of functions. So n minus 1 is what? 1. That's all. So this is what? 8. So you're getting the right answer here. So, but I thought there'll be, wait.
But sir, 3p2 into 2 would be 12, right?
So that, oh, right. Sorry, correct. So that's what. So this is, there should be double counting here. Thank you. So this is 12, and the right answer is 6. So these kind of functions get counted twice.
Okay.
So, yeah.
So half of that would be the right answer, right?
No,
but that not is half n. This n minus 1.
N factorial.
Yeah, upon means divide
divide
by,
into-
yes.
It just turns out to be half and double counting, but I mean, there is multiple counting in general. So Animesh, did you get it?
Yes, sir. Yes, sir.
Okay, good.
Thank you.
Okay, I'll take one more question, maybe. Where is this? Okay, guys. So there are no more questions. Then see you later. Bye then. I'll stop sharing.